Hello, 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 hello. Good to see you all. Hold on, what is happening here? Hang on one second. Oh, I see. I see. Hold on. Yes, hello. Thank you, Brand. Okay, sorry. Yes, thank you, Brandon, and thank you, Gabriella. I mean, hello, hello. Thank you, Brandon. Thank you, Gabriella. Um, Good afternoon, Kaya. I just skipped someone. Wait, I'm in the chat. Okay, the chat wasn't. Oh, sorry, that was a direct chat. Okay, well, yes. Hello, and good afternoon, Yaneli. Good afternoon, Kaya. Good afternoon, Ariana. Good afternoon, Genesis. Thank you for coming early. Um, Good afternoon, Roger. Excellent. Um, Where's some avatars or video here? Come up or whatever. I know it's plus I look different every time, so it's like, who is that guy? Blah blah blah. All right. So hello everybody. More people come. Um, um, all right. It's been a while. Good afternoon, John. Thank you. And more thank you. Uh, Here, I'll do this in the chat again. More people are coming in. Um, okay. So we some catching up some loose ends and catching up items here. So again, you've been working a lot lately and very hard, and you are now in more ways than one. You guys are very much ahead of me now. So good afternoon, Sanam. Thank you. So some announcements and logistics. This is partly by way of apology, but just more just for clarity. Um, and I'm speaking to most of you. I mean, I'm looking at the names. Like you are not behind. You might feel behind. You are not behind. I'm behind you. That is, first of all, I owe you these exams. They do take a while under even normal circumstances. These circumstances lately have not been totally normal for me, as you know. So I just ask your patience and to bear with me. You will get them back, of course. And I'm not going to hold on to them arbitrarily, but it will take a while, or it is taking a while. So just and we're just going to keep proceeding on with the course, with the exams getting graded in the. So I thank you for your patience, and I appreciate your patience, um, and the ball's in my court with the exams. That's number one. But number two, I realize like you've been working very hard at staying advanced, progressing through the material, even even while I have not been here or we haven't had discussions on all this material that you've been asked to think about. In other words, I'm very aware that you did this long, hard Newton's law homework before we really had a chance to talk about much of it. That's one thing that sort of often happens. But then there was this next homework that got assigned to you that was in Google Classroom about work done by non-constant forces. Now, to be totally honest, that I didn't even that was sort of I put that in Google Classroom way at the beginning of the semester and didn't realize, didn't check the dates or catch up with myself. So the truth of the matter is that work done by constant forces homework got assigned a little bit prematurely to you while I was in the hospital and everything, and I didn't quite even realize that was happening. Some of you made it clear to me. So thank you. So first of all, congratulations to those of you who even tried that homework number 9 without any discussion about work or anything. Like that's amazing. Good for you. And as you notice, if you did that already, out of the 24 points or whatever it was worth, you've already gotten 20 of them. And if I never get a chance to give you specific feedback or like so again with that, the ball's in my court. The remaining 4 points, you're either going to get feedback for and you'll figure out how to adjust it, or you're just going to get the 4 points, or in some cases you might not even be that worried about it anyway. Like you, the fact that you did it at all is amazing, and we'll get to that when we get to it. I'm impressed. It's duly noted that you are staying ahead and on top even when I'm not. Um, and those of you who have not done, if you looked at it and you're like, I don't even know how to do this, like, what is it? Fair enough. So everybody still has plenty of time to do that homework. Homework number 9, I'm talking about. Okay. I haven't readjusted the dates yet because I'm still catching up. But if your biggest concern in life is that you have not done homework 9 yet, don't be, you still totally can do it for sure. Now, similarly, even with homework 8 was meant to be assignment. It was hard and it's long and there's still a lot to talk about with it. Um, so certainly, so you already automatically got like 51 points out of the 65 for even just turning it in. Again, there too, if you've already seen 51 out of 65 points, it means you're waiting for either more feedback to tell you what to do to get the other 14 points, or you're waiting to get the other 14 points. The ball is in my court. Okay. You're not just going to be left with a 59 with no explanation, a 51. Like I hope you understand what I'm saying. If you got a 51 on the Newton's Law homework 8, okay, that's not a final score. It's a recognition and a thanks for being so responsible. You're either going to get feedback and see how to turn it to a 65, or it's going to turn into a 65. Okay, so what I'm saying to all of you is from here on in for a while, you're not going to get new things landing on your plate. Like we're about to enter into that zone of soon Thanksgiving, and then suddenly it's final exams and all that stuff. You've done a lot of work already. You've done some work that was disproportionately difficult. So now, the ball's in my court to catch up with you and try to get this material straight. And B, the ball's in your court to catch up. All of you have time before Thanksgiving and stuff to start tying up loose ends and looking back on anything where you did get feedback and you can improve, or anything that you never turned in that you could still turn in for some points, right? You're not going to get new things for a while. You're not going to get new in lecture. You're not going to get new demands or new assignments in lecture for a while. It's my time to try to catch up with you, and it's your time to catch up on anything that still could be caught up on for me. First of all, if that, thank you, Alfred. Okay, that's great. No, honestly, thank you for saying thank you, Alfred. For sure. Number one, you can submit for points for that for closing a conversational path. But also, no, good, good. I'm glad that means you understand what I'm saying. Good. Okay, I appreciate your appreciation. And I mean it. Yeah. Okay. So I'll assume that that's sort of clear. So, and again, there's nothing, guys. I mean, there's no assignment that you still couldn't get more points on, all of you. I hope that's clear. I think it's clear from Alfred's recognition. So right, it's about catch up now in a way for all of us for this pre-Thanksgiving period before everything gets super crazy. Hold on, I'm just now what that means to me, for me here. Oh, well, yeah, what that means on a concrete, oh God, sorry, things keep popping up. Okay. What that means on a concrete level is Newton's laws, forces. Like that's a big topic, right? You had a big homework about it. It does frame physics for like the rest of physics into physics 204 and all that. Like forces are very important. And I know you've got this big lab going on. If I correct me if I'm wrong on this, I believe that you're in the middle of lab 5 in the lab portion of this course. And is that correct, by the way, that you're in the middle of lab 5 and the big report for lab 5 is not due? Yes. Okay. Thank you, Alfred. Alfred's totally on this. Thank you. Thank you, Sonam. Awesome. Okay. And am I right that the big report for it, it's not due this week, it's like due next week or some it's not due like tomorrow or something. Is that correct? Or okay, I'm going to assume it's a two lab, right? Is it two? Right. Okay. So yes. Okay. Good. 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 So I'll tell you where my head is right now for the next couple of classes. Again, there's no new work. We're trying to catch up intellectually. So what I want to do is I want to back up and try to explain forces, how to draw diagrams, but specifically how to solve problems with F net equals MA. Like everything from here on in the math of physics all becomes the math of F net equals ma, of Newton's second law. That's where all the action is, like for the rest of physics in a way. And that requires understanding what forces are acting on what, when, how. Like the big issue now is identifying forces so that you could put them together mathematically and solve for F net equals ma. That means in general, but specifically in your lab. Your lab is it's a very good lab. It's one of my favorite labs, but it's very hard and it's very confusing until it isn't. I mean, or in my experience, like it's very hard to know. It's like a lot all at once, the lab. So my goal is in the next couple of classes to focus in on, also I'm going to screen share here. I'm going to use, bear with me for a second. I'm going to use, yeah, I'm going to use this problem right here from your recent homework. I'm just going to skip right to this problem right here, multi-force, the one on the screen right now. I'm going to use it to focus on, to sort of back up and explain like how all of this F net equals ma stuff works. I'm going to start by focusing on this and then branch from it by Wednesday, add layers and layers to this problem to show you how it ultimately relates to your lab. Okay, so I'm going to try to I'm going to try to help you with your lab report, in other words. So ultimately, your lab is like this problem. It's like an object on a surface, except the surface is tilted and the surface is rough, right? So by the time you get to lab, what you're analyzing is how does all this stuff work once we're involving angles and friction? Well, that's a lot. So I'm going to today start by just backing up and being like, what's going on in the simple case first, and then we'll add the layers of the angle and the friction by Wednesday. Okay. And hopefully that will clarify a lot of what you're doing in the lab. Okay. So that's my goal. And this is all in recognition that I sort of feel like I know what you talked about with Professor Lou Wednesday. I know she went over some problems and things. So I'm trying not to be redundant, but I'm just trying to do that. If there's any major other, but okay, so I'm going to start analyzing this in a second. I'm going to switch the screens. I'm going to start analyzing this problem right here on the screen, um, bit by bit. My main focus is the diagrams and turning the diagrams into equations. But I will say, please, I can't emphasize enough. This is about me catching up and regrouping with you. This is not about trying to create new challenges or new material. This is about trying to really sort through the material that is piled up in front of us. So why I'm saying that over and over is not just to get the thanks, but is because this is definitely a day, and Wednesday is definitely a day where you really should feel free to stop me at any time and be like, wait, that's something I didn't get in the lab, or wait, that's what I need right there. Like, wait, could you back up on that issue? Or to stop me and say, yeah, no, we've saw Professor Lou told us that a million times. Like or like Professor Talley told us that. Like, if I'm dwelling on something, if I get stuck like I am right now, if I get stuck on something and you're like, no, that's what we get. Can you please move on to this other issue? Tell me in the chat. This is much more like, hopefully, the next 2 days, I mean for it to be more like recitation than like lecture, because you've been lectured at enough. And now there's stuff that we need to sort through. And the lab is hard. And it's okay. Hopefully, so please stop me in the chat with moving. Remember, there's two game portals. Like you can get points for asking me to move forward politely. You can get points for asking me to move back politely. Like, please do. Okay. But that said, this problem right here on the screen is what I'm going to turn my attention to. I'm using it as an example of the whole topic of forces in Newton's laws. Just give me a quick electronic hands if it's clear what I'm about. Can I switch screens and start drawing about this? Like, are we clear? Is this a good plan? Okay. Thank you, Matthew. Thank you, Gabriella. Thank you, Ariana. Thank you, Yaneli. Thank you, did I say Matthew? Thank you, Genesis. Thank you, Kaya. Okay, awesome. Good. Thank you, Brian. And again, but please, anything in the chat, and if you're worried, put in the direct chat, any feedback at all of like how we could do this better. Um, okay. Okay. Thank you, John. Awesome. All right, so I'm switching back and the meeting is being transcribed. Okay. Um, okay, so I'm switching back. Sure. Okay. Okay. Oh, that was interesting. Okay. Okay. Wait. Hello. 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 Okay. Okay. So I'm going to that problem. Wow, there's a lot of latency. Okay. Okay. So I'm just going to switch to view. So homework A, like the Newton's laws, third multi-force round. Okay. So first it says that there's an apple on a table. It asks me to just draw a picture. There's my picture of an apple on a table. Notice, um, right from the start, I am labeling that apple with the letter M. Like, I just want to emphasize, like, there's always in every one of these problems, there's a bunch of objects always, and they all play roles, but there's always one object that we're focusing on, like the center of our attention is always one object, and that one object is literally the M in F net equals MA. Like literally what this is all about, always, even or especially your lab. There is always one mass whose acceleration we ultimately want to predict. In fact, let me even back up for a second and say, like, everything that you've been doing for the whole course until now, like everything that got involved in your midterm exam, all of those details, what they were really about is saying what physicists want to do is predict where something is going to be when. Like we always want to predict what point in space some object is going to be at some point in time. Or if we're using physics to solve crimes, we want to retrodict, we want to predict in the past where some object was at some past point in time, right? But it's all about where in space are you in time, always. So the big first thrust of physics, all the time that you've already spent grinding all these equations and concepts and everything, was all about realizing the big recognition of, oh, if at some point in space and at some point in time, we know the acceleration of a mass, then from the acceleration, we can predict the velocity and ultimately then the displacement or the position in time. Like if we know the acceleration, we could say x equals 1f at squared plus v naught t. And if we know the acceleration in these dimensions, we could do vector addition to get the acceleration in those dimensions. Like all of the stuff, vectors, calculus, all that stuff was really about analyzing and unpacking the implications of acceleration. We were believing that to know the acceleration of a mass was the key piece of information to know in order to predict the future or the past motion of that mass. Okay. That's what we've been. Now, what we're finally saying is, oh, okay, acceleration is like huge in physics and it's related to velocity, but it's not the same as velocity. Okay. So that's what all of this, like, all of our heads have been concerned with. But now we say, but how do we know the acceleration in the first place? Where did the acceleration come from? Like acceleration is an effect. What's the cause? Now we're saying the cause of acceleration is net force. What we're now saying is it's not only do we want always to know the acceleration of a mass, but we can find it out now if we identify all of the forces acting on a mass. If you identify all the forces acting on a mass in all the different directions, in all the different axes, and you deploy vector understandings, and you realize that acceleration is not the same thing as velocity. Sorry, I didn't even mean to say that, but it's true. But if you add up all of the forces acting on an object, then where all the action is now is this law down here at the bottom, Newton's second law, right? It says if you correctly identify every magnitude and every direction of every force acting on on a mass at a given point, at a given point in space, at a given point in time, then you will know the acceleration of that mass at that point in space, at that point in time. And then once you know the acceleration, it goes back to all the early physics. Once you know the acceleration, you can plug it into all the stuff that we were studying before. So it's all about F net equals MA now. That's where all the math from here on in is about F net equals MA, Newton's second law. But the key difficulty for everybody, for students or physicists, the key issue we all get, okay, if I add up all the F's and divide by M, I'll have the A. That's the program now. If I add up all the F's and I divide by M, I'll have the A, which is what I have learned I need in physics is the A. Well, I mean, the acceleration. But the issue for everybody, not just you, the issue for everybody is how do I know what all the F's are? And how do I know what their magnitudes and directions are? So the answer, it turns out, and that's where the thinking comes in, right? That's where it's physics, not just math. That's why you might still be somewhat confused or concerned, particularly in the lab. Like, what are all these forces? But here's the deal. Sorry, here's the deal is there's a method of drawing pictures in stages, where if you literally follow the rules of drawing the pictures, the following the rules will get you without having to be creative or without having to be brilliant. Following the rules of drawing the pictures will get you stage by stage to the point where you have a correct left side of Newton's second law all written out for each axis. Like, again, I know I'm taking too long to get to this in a way, but what I didn't realize for years is that these pictures, these system schemas that I'm now going to talk with you about, and then these pure free body diagrams, and then these component free body diagrams, it's like 3 stages of pictures. They're not just rough sketches just to give you an idea. And they're not just busy work to give you a grade. What they are is the setup. It is the setup to ensure that the correct math will then be done. The one thing maybe we want you to have learned before we go into all of this, or to have noticed now that you've taken a midterm, is that the issue in physics isn't really the math, right? I think most of you have probably already knew this or noticed that you thought you were scared of the math. Maybe some of you thought that the scary thing of physics, and maybe still, I'm not saying math is easy, but I think a lot of you have noticed that really once you set up a problem in physics, once it's set up correctly, the math often takes care of itself. You wouldn't be in this science class. You wouldn't have gotten this far in science if you hadn't already gotten somewhat practiced in algebra or trigonometry or even calculus in many of your cases, right? That's not really where the issue is. The issue is how do I set things up so that the math crank can do its thing, right? And that's why with the 5-step method, we've been having you practice like it's real. Step 4, by the time you get to step 4, that's not the hard part. The hard part is what do you put down to get yourself to step 4, right? All right, anyway, I'm over talking. So what I'm saying is here now, you've been practicing where it's hard, where you have to make decisions about what to put down for step 3, the GDPs. That's hard for for all of us. You have to actually make decisions to set up the math. I'm telling you right now, if you take these diagrams, these pictures seriously, if you let yourself and me be like kindergartners and just like not try to be creative or not try to be brilliant or not try to be insightful and just literally take these pictures as serious pieces of the program, then following the rules behind the pictures will literally ensure that that F net is set up correctly on each axis, and then all you have to do is divide by M, and you'll get the A on every axis, which is the goal. So, okay, so we're going to deal with the pictures now, and forgive me if some of it's redundant or whatever, but it's all about the pictures now. Okay, I know. Um, so we've got an apple on a table. um, that's just a picture. Like step 1 DFP. Okay, but now it asks for a system schema of the apple. What does that even mean? Okay, the system schema is where we first are trying to identify every force that is acting on that mass, on the mass that will be our object of focus, like the apple, which I'm now calling M from here on in, the M of F net equals MA. We want to find out every single force that is acting on that mass. And the way we find out, and it seems like a hard decision for all of us until we get used to it, the way we find out every force acting on the mass, well, is we draw a system schema. And the way we draw a system schema is we ask ourselves, what are all of the other actual real material objects in the universe that are interacting with this mass? That is, we remember right from the get-go, and this is a point of the system, that a force is an interaction between two objects. If I think that there's a force acting on my apple, that must mean that if I think that there's one force acting on my apple, then there's got to be one other object in the world, somewhere in the universe, that is interacting with my apple. In other words, we cannot make, even though people do all the time and want to do all this all the time, we cannot make up forces. Forces are not magical. I mean, in physics, forces are not magical. Forces don't come out of thin air, and a force is not something that I have. A force is something that something does to me. So if the first issue is what are the forces acting on this apple, what we say with the system schema is we ask, what are the other objects in the world acting on this apple, interacting with this apple? More specifically, what are the other objects in the world pushing or pulling on this apple? Literally pushing or pulling on this apple. Now, so we're going to draw a solid, so we draw a dotted circle for the M itself, like I've always in every system schema. I draw a dotted circle for the M itself. And then I'm going to draw a solid circle for every object in the world that I believe is interacting with my apple. How do I know what objects are interacting with it? I ask what other objects in the world are pushing or pulling it. How do I know what objects are pushing or pulling it? Well, there's an even more, I'm going to turn the page in a moment, but there's a specific answer to that question. It all sounds very vague until it doesn't. The first answer is the entire Earth, or what you could call center of Earth, either way. The entire, as you know as you have heard, the entire Earth is always below our feet. It's always there. And somehow the entire Earth has, sorry, I'm just looking at the chat. The entire Earth seems to have this capacity, this ability to pull on things always, to pull on everything near its surface without touching. I don't quite yet, I mean, we don't quite yet know how or why it does that. I mean, Galileo didn't quite know why or how it did that. Newton, when he's first developing all this stuff, doesn't quite know how or why it does that. Then he has some ideas, but then even by the time we get to Einstein in like 1915, we still, as human beings, are very confused always about exactly why and how Earth has this ability that we call gravity to pull on everything toward it, toward its center. The entire mass of Earth seems to pull everything near it towards its center. Now, I'm not trying to, I am making a big deal because it is a big deal. I'm not trying to confuse you. Here's where I'm going with this. I'm saying the Earth is one important exception that's so important that it's in every single diagram and in every situation. What do I mean when I call it? So it's always there. So the first object you can always draw a solid circle for, you can always put entire Earth into every single system schema, no matter, including the lab situation, because the Earth is always there and the Earth is always pulling on whatever mass you're focusing on. The reason I would put it first always is A, because it's always there, but B, because what's really mysterious and interesting about the Earth is it somehow has the ability to do this without touching, without touching. And the reason I'm saying that very loudly, and I'll say it again, the Earth pulls on objects without touching them. Now you know that. I mean, you've experienced that your whole life, and all people that have studied physics have experienced that for thousands of years. We all know it. We all know it's true, even if we don't quite know why or how. But we know it's true once we identify that truth. Now we can move on and say, from here on, other than the Earth, if you want to know, and this is very important, I cannot emphasize what I'm about to say enough. From other than the Earth, every single object that will possibly go in your system schema or every single arrow that will possibly go in your free body diagram should only be representing objects that are touching the mass. Like once you draw the Earth, and I did, right? The solid circle that says EE, I've drawn the entire Earth, or you could say CE for center of Earth, or you could say PE for planet Earth, whatever. Once you've drawn a solid circle that represents Earth, that is the only object at all that you should ever recognize as interacting without touching. Every other than that, the test, if you're asking yourself, is there a force? The answer is, well, is something touching my object? If yes, then there's a force. If no, then it's not exerting a force. It's all about touching. Literally. I'm going to say that one more time, then I'm going to move on. The test of whether to draw an object, whether to identify some other object as interacting with yours, the question of whether some other, no matter how complicated, even the lab, even when things get really complicated, when you're identifying what is exerting a force on my object, on my mass, the answer is anything touching it plus planet Earth. Okay. So I put the table in here. The table is the one other object in the world that is interacting with the apple. How do I know the table's interacting with the apple? Because it's touching it. It's literally like underneath the apple, like in physical contact with the apple. Okay. And then I ask so I'm back to the problem, right? I'm in this problem, homework, whatever, number 3A, right? The apple on the table. Um, so in the system schema, I've drawn the Earth, solid circle, because it's pulling gravitationally on my mass. And then I've drawn a table, solid circle, because it's interacting by touching my mass. And then I stop and ask myself, is anything else touching my mass? Is anything else touching the apple? Is anything touching the apple? And the answer is no. There's nothing else that was, there could have been, like in the lab. Oh, yeah, no. That's awesome. Awesome. Thank you. That's total points right there, Jordan. Thanks. Someone's still paying attention. That's great. I mean, I'm great. Like don't get me like I'm giving you right now, I'm analyzing this example and we're going to make it more and more complicated as we adapt it to the lab, but I'm just giving you the rules in general. There could be a million other, like there could be an apple on the table that someone's touching with their finger or pulling with a string. Other things could be happening, but in this case they told us it's just an apple on a table, so there's no thing else touching the apple, therefore nothing else goes in the diagram. So in this diagram, the system schema, you're literally just drawing objects that are touching yours plus planet Earth, okay? So that's the first rule, is you just draw a solid circle for anything and everything that's touching your object, plus a solid circle for the entire Earth. And I'm going to obviously turn the page in a second. And you could draw those solid circles wherever you want. This is literally about identification. Again, the reason I'm so over talking this, and I do sort of apologize, sort of, is that really everything I'm talking about right now is how do you know whether something's a force or not? And honestly, that is the thing that confuses everybody for a long time. How do I know whether, or even people that think they're not confused, they make mistakes on this all the time. The issue is whether something's a force or not. And the simple answer ultimately is it's if it's either Earth or it's touching, then it's a force. And if not, then not. It's actually that simple. And that's all the diagram is trying to convey. Almost all. We're not worrying about directions. We're not worrying about magnitudes. And that's okay. We're just worried about what are the objects interacting. And we're using unfancy words like table and Earth. Okay. Now we go to the next thing. Yeah. So this next page is everything I just said for like a million years. So right. So how do you know what's interacting? Anything that's touching plus the entire Earth. And whatever that entire Earth is doing to an object, we call the gravitational force, or in fact, we call, oops, sorry. I'll say more about this on the next page, but like, well, I probably should, it doesn't matter. All right. So that's that. Now, the next thing you do in the diagram, now, okay, I have to admit, This is a little, the next thing I'm going to say is largely simple, but there's one very confusing aspect to it. So bear with me and definitely ask questions when I get to the confusing bit, to the exception, um, because it is important. So the one thing I'm sure you noticed in my picture 2 pages ago, I'll turn back to it in a second. I'm sure you noticed that I didn't just have circles. There was also lines in the picture. Okay, now the lines are really the issue. The purpose of drawing the circles, the purpose of drawing the circles was to force us. Yeah, let me say this a different way. The ultimate purpose of the system schema is the lines. What we're really trying to do with the system schema is get lines drawn because then the lines represent forces. We're trying to identify forces. Every line represents a force. Then we use those lines to make our next picture, which is called the free body diagram. Every line in the system schema becomes a vector arrow in the free body diagram. And the vector arrows then start doing the math for us, right? So what we really want, we want to make sure that every single force that's actually acting has a vector arrow representing it and then to be plugged into the math. We also want to make sure that every force gets represented and captured through a vector arrow in the math, hence the free body diagram. We also, almost as important, want to make sure that no vector arrows get into the math that represent fake or imaginary forces, which people do all the time. We don't want non-real forces to accidentally get mathematically captured. So the reason we're doing the system schema is to force ourselves to draw lines that we're very confident of. And then we say whatever is a line is actually a force that we're confident of. And we're going to turn that line into a vector arrow in the next diagram. So the purpose of this system schema is really the lines. But how we believe in the lines is the circles that we draw. We don't believe in a line unless it came from a circle. So let's take notice, for example, the line between Earth and the mass. Notice that that is just a line. It's trying to emphasize Newton's third law. It's trying to say, look, Earth is pulling on the mass is pulling on the Earth. It's a mutual interaction. It's a mutual interaction. It's a tug of war. Earth is pulling on mass is pulling on Earth. If that's all I cared about, if I just wanted to know, uh, like, put it, it's not pulling on the mass any more than it's pulling on the Earth. And that line is not. So it's trying to represent the mutuality of Newton's third law. We're going to turn it into an arrow that's just focused on the mass once we get to the free body diagram. But you'll notice, but how do you know how to draw the lines? You notice that I have two lines on the right part of the diagram. That's a little bit tricky. So here's the deal with the lines. The big rule when you're drawing lines is the one touch, one line rule. The big overarching rule, especially when things get very complicated, and it's always, well, anyway, especially when things get very complicated, like the lab, is that for every touch, you draw a line. However, there's two exceptions to that rule. And there's only two. There's exactly two. There's no other exceptions. And if you literally understand this rule and you literally understand the two exceptions, then you'll understand, then you have the whole program. But the exceptions are subtle. Exception one is what we already have said, luckily. Exception one is that gravity is an interaction that doesn't involve touching. So gravity is exception one in every single diagram where you get a line, even though there's no touching there. Okay, that's an exception. Normally, I'm saying in order for there to be a line, there's got to be a touch. Well, gravity is exception one. There's no touch, but there is a line. But again, even though it's an exception to the rule, the exception applies every single diagram, so you can memorize it or whatever, and it'll never fail you. The other exception is far more confusing, and we need it to understand it for the lab. The other exception is when two surfaces are pressing against each other, specifically when two potentially rough surfaces are pressing against each other. Now, again, you might want to add more notes to this right now, like, and screenshot them and send it to me for points. Like, when I say two rough surfaces pressing against each other, I mean just that. I mean surfaces. So I mean like two-dimensional planes, like areas of material. And I mean pressing against each other. And I mean areas that might be rough, like might have texture to them. So what do I not mean? I don't mean like a string pulling on a fish. In fact, I would really urge you, and I'm explicitly urging you, if you write down this just to make it clear in your mind and screenshot it for, I'll be so happy if you screenshot it for points. I'm saying like pulling up on a fish with a fish line. If you're going fishing, right, and there's a fish in the water, and you put a line, like you attach a line with a hook to that fish, and you pull the fish up with that line, with that fishing string, fishing rope, fishing line. That would be an example, a perfect, clean example of the one touch, one line rule. If the string is pulling up on the fish, it's touching the fish, the string would go into the into the system schema. Like, okay, again, this is a different example now, but this is why I'm not writing it down. But if you can follow me, I'm saying a perfect example of a clean one touch, one line situation would be a fish being pulled up by a fishing line. The fit in that system schema, we would have a circle for planet Earth. We would, because planet Earth's always there. We'd have a solid circle for planet Earth. We would have a dotted circle for the mass of the fish. We would have a solid circle for the rope, the string pulling up on the fish. We would, because that's another object touching the fish, right? And in that situation, we would connect the rope. So we would have a solid circle for the rope or for the fishing line, and we would connect it to the fish with one line because the fishing rope is touching the fish and it's just touching it in a simple, everyday pull kind of way. So it would get one line in the system schema that would then eventually become one vector arrow in our free body diagram. Okay, that is a clean case of one touch, one line rule. What I'm talking about here in B, that is much more confusing, but super common, super important to talk about. I'm talking about not if you're pulling on something. I'm talking about if two rough surfaces are pressing against each other. Like the apple is probably a rough surface pressing against the table, or in the lab, your the marble or whatever it is like has a bottom surface that's somewhat maybe not perfectly smooth, pressing against the track of the lab, right? When you have surfaces pushing against each other, then we generally in the system schema, if we until we learn a bunch of new details, we would be conservative and draw two lines, even though there seems to be one touch. When the one touch is two surfaces pressing against each other, we draw two lines, and I'll tell you why. Because when two rough surfaces press against each other in any way, if two possibly rough, realistic surfaces press against each other, like my two hands are pressing against each other, then by pushing, if they're rough, if I looked at them really closely, if I zoomed in with like a microscope, I would see all these nudges and like nooks and crannies and like bumps and ridges on the surface of each of my hands, right? And so when they press against each other this way, against each other, they also they lock into each other like the teeth of two combs pressing against each other. They lock into each other. So they automatically make it difficult for me to rub my hands or slide my hands against each other, along each other. Do you see what I'm saying? That in the real world of rough surfaces pressing against each other, By pressing two surfaces against, you also make it difficult for them to slide along each other. Wait, first of all, I'm going to stop right there. First of all, just honestly, just do a quick electronic hands. If what I'm saying so far is with rough surfaces, when they thank you, Gabrielle. That's good enough for me. Thank you. I didn't even finish. Thank you, Jaron. Okay. All right. Awesome. Okay. So great. And there's more. Roger. Thank you, Ariana. I think, or Jen. Thank you. I don't see you all, but I see you. Great. It is Roger. Yes. And Genesis and Kaya. Thank you. Okay. Means a lot. Really, really. So why am I saying all this? Because it is confusing. This is like in a weird, like the heart of. But what I'm saying is then the one in general, it's all about touching, backing up. What I'm trying to emphasize here is when you're trying to figure out what's a force, what's not a force, what forces do I count, what it's all about touching, other than gravity. Like gravity is an exception. It's always there. It's not touching. I don't know why. Like Einstein didn't even know why. Like honestly. So I'm not trying to trick you. I'm just saying, put gravity over there for the moment. It somehow it pulls without touching. But then over here now, like whenever something touches in a straightforward, like pulley, stringy kind of way, then it's a touch, it's a force, it's one and one, end of story. When things press against each other, when surfaces press against each other, which happens all the time in the real world, that's why I'm spending so much time on this. When surfaces press against each other in the real world, by going like this, they automatically also make it hard to go like that. So, uh, when we don't know all the details of the numbers or whatever, to cover ourselves, to be conservative, to make sure in a system schema, if I see that a table is pressing against an apple, until I specifically know or specifically can convince myself that the table is so smooth that it's not really going to have a hard time rubbing against the apple, or if I specifically know later on, oh, the apple's not even sliding anyway, so I don't even care. Until I'm sure of all of that, which sometimes I am and sometimes I'm not, I put two lines in the system schema, two lines. One represents this kind of force, this pressing against, and one represents the pressing along, the sliding along. Okay. Because again, what's my ultimate goal? My goal is I want a line for every possible thing that might possibly be a force in the free body diagram and in the math. I want to see a line in the system schema because in a minute, when I shut up about all this, in a minute, the purpose of all this discussion is I'm just going to pull the lines out of the system schema and make a new diagram from them. Everything else is going to disappear. Everything else was just to be careful about generating the lines. So once I'm confident in my lines, I'm going to pull them out and make a new picture from them. So that's why I'm obsessing over them. Okay. And what I'm saying right now is in the absence of any other information, I think now that because there was gravity, because there was planet Earth, that's one force. And then because there's a table pushing against my apple, there's potentially two forces. One going like, sorry, since there was a table underneath my apple, there's one force potentially going like this against my apple, and one force potentially going like this along my apple. Now, again, maybe that one's going to disappear if we learn enough about the smoothness of the apple or something. But potentially I have this and I have this. Okay. And I have names for those. Wait, do I want to say this? Well, yeah. Yeah. From now on, this force, the like whenever two plane surfaces are pressing against each other, picture that there's what we call the plane of contact between the two surfaces. Maybe write this down if you like if two surfaces are like two pieces of bread and you're making a turkey sandwich, so like the thin slice of turkey between the two pieces of bread is like the plane of contact. It's the Euclidean plane or the geometric area that both pieces of bread are like pressing against. And notice, like, however you turn your sandwich, you turn the plane of contact with you. So even if you're holding your sandwich vertically, I don't know why you would do this, but if you're holding a sandwich like this, the plane of contact, the turkey would be like that, right? And if you're holding the sandwich on an angle, like you do in the lab, then the plane of contact would be on an angle, right? So whatever the force is pushing on, whatever force is pushing perpendicular to the plane of contact, we call the normal force. That's what's written here to the side in white, right? The normal force just means the force of pressing the you could almost say the pressure, but it's the force of one surface pushing on another surface perpendicular to the plane of contact. In mathematics and physics, the word normal just means perpendicular. So the normal force just means the perpendicular component of this phenomenon, this pressure phenomenon between two surfaces. The parallel component is called friction. What I'm trying to emphasize right now, before I go any further, is that when surfaces press against each other, and again, this is what becomes hard in the lab in a way, part of what becomes hard. When surfaces press against each other this way, they automatically create some kind of force that way. This is called the normal force. This is called the friction force. The normal and the friction are just two components of this overall sandwiching phenomenon. Okay. The reason to focus on the word normal force is you won't have friction unless you have a normal force. Like when I pull a fish up with a string, there's no normal, there's no friction. Like normal doesn't always, and when something is free falling, if I just drop an apple, if I just drop an apple that's just free falling to the ground, certainly the apple has weight. Certainly planet Earth is pulling down on the apple. But if the apple is just free falling, then nothing is pressing against it, nothing is touching it. So there's no normal force at all, and there's no friction. What I'm trying to emphasize here uh, is you really only want to identify forces when there's touching. And if there's touching of this kind, you want to recognize that one kind of touch could bring another kind of touch. That pairing is called the normal force with friction, but don't introduce it unless you're sure it's there. Um, so, okay, I'm gonna go. I know I'm saying so. Summary: you draw the objects in the system schema that you think are interacting with your object. Those objects are Earth plus anything touching your object. Then, for every single touch, you draw a line. For every single touch, you draw a line in your system schema. But also, for gravity, for planet Earth, you draw a line, even though there's no touch. And for any touch you see that's like this, you conservatively draw two lines to account for the fact that this might also bring along that. Okay? Now we move on. I mean, stop me if you don't want me to. Honestly, I know this it's a lot of words for very vague abstract concept. Now we're going to take our lines and turn them into a free body diagram, a what we call a pure free body diagram first. Then from the pure free body diagram, we're going to divide vectors into components and make a component free body diagram. But first, we're drawing a pure free body diagram. So, like I was saying a minute ago, every line from our system schema is now going to become a vector arrow in our FBD. The M circle is going to become a point. So we're now getting more mathematical. We're now focusing all our attention just like on the center of our mass, calling it a point that exists in a point in space at a point in time. And every one of those lines, we're now going to turn into a vector that starts its tail at our point and emanates out and points in a particular direction. And everything else is going to be gone from our original system schema. I'm even going to say too, I'll even add one thing. Okay. Um, so one other thing I just added in handwriting here, point number 5 is the names of the objects that were in our old picture, our system schema, will now be substituted out and will have names of forces. This is where this vocabulary like friction force, normal force, or weight, or mg now comes into play. And again, I want to caution you, don't jump the gun on this stuff. Like In the first picture, I didn't use words like normal force or friction force even if I know you know those words or you've been hearing them, but I'm not holding back on you. I'm holding back on myself. Like in the first picture, I never use those words because the first picture is trying to force me to only identify forces if I can identify the actual regular everyday objects that are generating those forces. Okay. Once I'm satisfied that I've done that in the first, and that's why in the first picture, I'm not caring about direction or fancy names or anything like that. It's just like what is going on in the system schema. Now that I trust my system schema because I carefully drew circles and I carefully counted up lines or yeah, counted up lines. Now I say, okay, I'm going to make a new picture here. I'm going to make a new picture where first of all, my object of focus, my mass is just like this little point at a point in space and at a point in time. And now every one of those lines becomes an arrow emanating from this point. And now every one of those names of those objects, now I'm using a fancy name for a force. And there's a it's not trying to be fancy, but now I'm saying now if I really believe that my object is experiencing these various forces, if I'm confident that the forces are acting, now I no longer care where the forces came from. Now I just want to know what type of forces are they and how do they behave. Like, so now I'm fully like zoomed in, laser focused on my mass at a point in space, at a point in time, what forces are acting on it. So now I introduce more technical terms for these forces. Notice one thing before I even get into those names. Notice, well, okay, actually, that's even confusing. Here, I'll just leave it as I'll just leave it here. Here's oh, hang on one second. Oh, sorry, bear with me for a second. I'm pause recording for okay. Um, so the first thing I want to emphasize, and I know we have 16 minutes. First thing I want to emphasize is in principle, every single one of those lines now has to become an arrow here. Again, that's the whole purpose of the other thing is if there's three lines, there better be three arrows here. But and, and we start now giving them directions and making them into specific vectors, right? But I want to address first because the whole friction thing is like the hardest thing of all of this. And again, it is the emphasis of your lab. So two surfaces were pressing against each other. So we acknowledge the possibility that if they were going like this, that they could be going like this. Now, this business, or in this case, the table is pushing up on the apple. So the table is pushing up on the apple. That is what we call the normal force. So I have an upward arrow labeled N, um, meaning that the table is pushing up on the mass. N stands for normal force, right? And again, let me say, it's not normal. Normal doesn't mean it's always there. It's not always there in every single situation. If the apple were just free falling down, there would be no normal force. Normal means perpendicular. It means that the table is pushing perpendicularly against the plane of contact formed between the table and the apple. The table's pushing up. How do I know it's pushing? Because push means away and pull means toward. The table's not a magnet. It's not sucking the apple toward it. It's shoving it away. How do I know it's shoving it up? Because if the table weren't there, the apple would fall down, right? So the table is most assuredly pushing the apple up. That is what we call the normal force exerted by the table, right? A normal force could be exerted by a hand or a table or a platform, whatever. But now I don't care anymore that it's the table, so I'm just calling it the normal force. So I'm calling it the normal force. Now, the fact that there's a normal force up from the table, that's one line from my picture, means there's another line in my system schema that represented the possibility of friction, right? There's now could be sliding phenomenon between the table and the apple. That's what we would call friction. And that should be an arrow as well in this picture. For every line in that diagram, there should be an arrow in this picture. So I go and ask myself before I go further, okay, should there be an arrow somewhere on the horizontal axis representing friction? I mean, there should be realistically. But I read the problem really carefully. I go to ask myself the question, maybe I ask myself, how strong is the friction? Or even better, I ask myself, which direction would the friction be pushing in? I mean, it's certainly sliding along the table, but would it be like to the left or to the right? And the more I look at the problem, the more I realize I have zero particular reason to believe that the friction would be going left any more than it'd be going right. In other words, when I really look at the problem, I notice they didn't give me any information about how rough the tables are, unlike in the lab where you're very focused about how rough the surfaces are. And there's no issue of the apple move. The apple isn't even moving, and no one's even trying to get the apple to move. If there was any information at all, like the apple was sliding left or someone was trying to pull the apple to the right, if there was anything about the apple's x-axis motion or acceleration or anything about the apple's roughness, then I would take that second line, that third line from my system schema and turn it into an arrow right here, pointing in a particular direction on the x-axis. But there's no information at all, which leads me to believe, first of all, that the apple's probably very smooth. The table's probably really smooth, and the apple's never going anywhere for the entire problem. So friction is playing no role. So I can leave it out. I'm going to pause again. I'm going to move. So I'm saying again, the trickiness of friction is you always do you want the minute you're believing the minute you're accounting for surfaces pushing against each other, the minute you're starting to think about the normal force, you should think about the friction force possibilities, which means in the system schema, the minute there's this, there should be two lines to generate the thinking. But by the time you get to the free body diagram, if you're actively, you should be checking for all friction possible information. But if there's really no information at all to help with friction at all, then you can leave friction out of the free body diagram. So now we're down to 2 arrows instead of 3. I'm going to pause again because that's a lot. I know it's very vague, but do you sort of follow what I'm like? Raise your hand if you sort of follow what I'm saying about, like, basically what I'm saying is I'm saying this. Oh, I just heard that. That's great. I'm saying, great. Thank you, Jaron. All right. It's all about Jaron today. And someone else and Samantha. Thank you so much. Okay. And Kaya, thank you so much. Okay. All right. Uh, Okay, I'm even, you know what, even just to make this slightly more, the reason I'm getting so tongue-tied about friction and everything, and I'll get more concrete about it Wednesday, but in the lab, the main thing you ultimately need to understand is that friction equals mu times the normal force. Mu is the how rough the surfaces are. Like I don't want to I don't want to rabbit hole myself right now. But the ultimate way to get friction is to multiply the roughness times the normal. So you need to be able to understand the normal in order to do that. So right now my focus is on the normal and what it's all about. But I'm just trying to constantly keep you alerted to how it subtly turns into friction calculations. But right here in this problem, there isn't friction yet. So I'm going one step at a time. So anyway, all right. So here in this problem, I ignored the friction line. The other two lines, I'm turning into arrows. One line is the normal force of the table pushing up on to my apple. So that's called normal. That's an arrow pointing up. The other arrow is the downward pull of planet Earth, the downward pull called the gravitational pull of planet Earth, which we often call weight. So let's pause on that for a second. Like the word for it, the word for okay. Um, the pull that automatically seems to always be exerted by Earth onto any mass, we call weight. Weight is not the same thing as mass, as you've heard many times. Mass is measured in kilograms. Mass is the resist is mass is resistance to forces. Weight is itself a force. Weight is a specific force. It is the specific force of gravity acting on a mass. Okay. What I'm here to just, I know we have 6 minutes left, but I just want to emphasize now once and for, or try, is the weight. Like we're in the system schemas, we were just putting names of objects to identify them. Now we're trying to put names of forces that we can into our diagram that we can actually use in the math. So we're not even, so I'm saying we could put the name weight as the downward arrow due to gravity in our free body diagram. But we want to do even better than that. We want to put something down that's going to help us with the math. And it turns out that the weight, the force of weight on an object, the force measured in newtons that is always pulling down on an object from planet Earth is always equal to the object's mass, m, times that number 9.8 meters per second squared. Always. Why? Because consider free fall for, yeah, consider free fall for a second as a sidebar. Free fall is a situation where no forces are acting on an object other than gravity, other than weight, right? Like if the apple were free falling toward the earth, the free body diagram on it, the only arrow acting on it would be the arrow of weight, right? So if you add up all the forces acting on an object in free fall, there's only one force. It's the force of weight. So according to Newton's second law, weight would equal ma, right? If you're in free fall. If you're in free fall, weight, your weight equals your mass times your acceleration. But we know that if you're in free fall, your acceleration is g, that 9.8 number, right? If you're in free fall, whoever you are, whatever your mass is, you are falling always at an acceleration rate of 9.8 meters per second squared, right? Therefore, thus, the weight of an object is always m times g. It's not g and it's not m, it's m times g. I hope that. So always from now on. So in a free body diagram, always, just like in the system schema, there's always a solid circle, that means entire Earth, and there's always a line connecting to the map. That always just becomes a downward arrow called mg, always in every single free body diagram. And mg literally means the number of kilograms times 9.8 or 10 meters per second squared. Okay. And I know we're starting to run out of, we have 4 minutes left. I'm saying right now, this diagram is the free body diagram of the apple on the table. Soon we're going to turn this into what it would be if this were the marble on your track in the lab. In order to turn this into the marble on the track in your lab, I've got to add two aspects to this, right? First of all, I'm going to have to put this on an angle. And then second of all, I'm going to have to add friction. That's what's going to happen on Wednesday. But before I even do that, with 3 minutes left, I want to alert your attention to, yeah, the next question in the homework, which is very like part four of this question. I know we have 2 minutes now. Okay, I'm going to just do this very quickly. Like what you notice in the, I have 2 minutes. You notice in the diagram, there's two forces and they're opposite in direction and they look like they're equal in magnitude. In fact, they are equal in magnitude. But what I want to make clear right now, just going to write this and I'll explain it more on Wednesday if I have to, is that is not a Newton's third law pair. Like what I want to make clear right now is in terms of action and reaction, what that diagram means is, so we'll just write this and we'll call it a day. Um, the mg arrow means Earth pulls down on apple. That's what that arrow means. And therefore, by Newton's third law, automatically the apple pulls up. Sorry. Automatically, well, yeah, no, right. The apple pulls up on Earth. That is a pair. That is one arrow. In other words, that mg is an action. What's its reaction? Not the other arrow. Its reaction is the apple pulls back up on the Earth. That arrow is its own tug of war. Every force is its own tug of war. And similarly, at the same, and that would be there even if this thing were in free fall. If it's falling down, Earth would pull on apple down. And at the same time, apple would pull up on Earth. And that's what's implied by the line in the system. Okay, it's 1:30. At the same time, the normal force means table pushes up on apple. So apple pushes down, on table. I know it's class is over. You can go. I'm just trying to emphasize here, and then we'll continue Wednesday. Every single arrow is its own pair, its own action and reaction. Just because there's two arrows in the diagram that are opposite direction doesn't mean they have to be equal in magnitude. That's important for the lab too. Sorry, so I'm done. I'm gonna hang out. I'm gonna turn off the recording. If there's any, I know this was a lot and a little at the same time. Any questions, you can hang out for a minute and ask them for sure. But I'm turning off the recording and have a great, thank you. Yes, have a good night. Have a good night. Right. Exclamation point. I don't even know what that is. But okay.